In this video, we're going to be learning about a functional group that we call the carboxyl functional group, although most people simply refer to these as what we call organic acids because of their behavior when they're dropped into water, which we'll take a look at as the final component of this video. For now, in terms of recognizing their structure, we can see that just like aldehydes, these functional groups only fall on a terminal carbon because these are actually a combination of a carbonyl, which we can see from the double bonded oxygen on this terminal carbon here, and a hydroxyl group, also known as an alcohol. And again, because of the fact that this carbon has a double bonded oxygen and an OH group here, that means that this carbon requires 3 free bonds. So if we wanted to build a carboxyl functional group on an interior carbon, we can put the carbonyl group here and the alcohol here, and then you'd immediately recognize the problem that this carbon has 5 bonds, which means it is physically impossible to have a carboxyl functional group on anything other than a terminal carbon. Now, because carboxyls function as organic acids, we recognize these compounds with the suffix oic acid. So, for example, we can see the simplest form of oic acid is the one with 1 carbon, which we can name according to the prefix meth. And since it's physically impossible to have carbon-to-carbon double or triple bonds with 1 carbon, the parent molecule would be methane. And then we simply add oic acid to the suffix of methane like this. Now, because, just like aldehydes, because acids can only be found at carbon 1, or in the case of this molecule, at the first and final carbons of the parent chain, you will notice that it's completely unnecessary to list a location indicator here. So, for example, if we wanted to name this carboxylic acid based on butane, because again, we see that there are 4 carbons and only single carbon-to-carbon bonds here, we don't actually need to specify butane 1-oic acid. We can just write butanoic acid because it's implied that the functional group determines where carbon 1 is. And even in the case where an acid has 2 carboxylic acid functional groups or 2 carboxyl groups, we actually don't need to specify the locations here. So if we were to name this parent chain, it doesn't really matter which carbon we designate as carbon 1 because this molecule is symmetrical. So we would first identify this molecule in terms of its EZ configuration. So we can see that the longest carbon chains fall on opposite sides of the double bond, and since our double bond is in position 2, we would call this 2E at the beginning. And it has 4 carbons, so we designate it with the prefix but, and the double bond is in location 2, so we would simply call this 2E butene dioic acid, because once again, the acid functional groups need to fall on the first and last carbons, so identifying the location number for these would be redundant. Now, the final thing that we can discuss is actually how these behave as acids when they're dropped into water, and we can take a look at a simple organic acid like this molecule here. Now, because of oxygen's lone pairs and higher electronegativity than hydrogen, the OH group, as in the case of all OH groups, has a dipole on it, with the oxygen having a partial negative charge and the hydrogen having a partial positive charge. Now, when these acids are dropped into water, this allows the oxygen side of water to attract to the hydrogen with a positive pole like this. And when the water molecule actually gets close enough, it can use one of its lone pairs to form a bond with this hydrogen, causing this hydrogen to break off like this. So basically what happens is that the water molecule uses its lone pair to form a bond with this hydrogen here. But since hydrogen cannot make more than one bond, the existing bond is going to break and turn into a lone pair on this oxygen that used to be part of the alcohol group here. Now, we can see from this arrow that the electrons are moving from the bond to becoming a lone pair on this oxygen, meaning that this oxygen is gaining electrons, and we can see that the lone pair electrons are moving away from the oxygen in water, which means that this oxygen is losing electrons, which is why if we draw what happens to our two molecules when these act as an acid, our carboxyl group is going to look like this in the end, where this oxygen here that used to be the oxygen in the alcohol now has a negative charge because it has gained electrons that used to be in the bond holding the hydrogen there. Whereas on water, we see that it now has 3 hydrogens like this and only one lone pair, and because one of the lone pairs has moved away from the oxygen, that gives the oxygen a positive charge, and we have just made the hydronium ion, which is characteristic of every acid when added to water. So this is why we can call carboxyls organic acids, because they are organic in nature and their structure allows them to lose a hydrogen whenever they are added to water because of the polarity that the functional group adds. To test your knowledge of the nomenclature system of carboxylic acids, you can try the naming and drawing questions below.